Reaction quotient. At any time, the system can be sampled to determine the amount of the reactants and also product that is present at certain time. A ratio of the product to the reactants calculated in the same manner as K tells us whether the system has come to the equilibrium if the Q is equal to K, or the reaction has to proceed further from the reactant product, or in the reverse direction from product to the reactant. So the reaction quotient adopts the same expression as K, however the amount that we consider is not at the equilibrium. So if we have a general equation of the A plus B produce C plus D, okay, the value of the Q that we calculate can tell us whether the system is at the equilibrium or it is not at the equilibrium yet. If it is not at the equilibrium, to which direction the reaction will proceed in order for the system to establish the equilibrium. Concentration of the product and also reactant can be sampled at any time. If we look at to this figure, this is actually the decomposition reaction of the N2O4 to form NO2. So the concentration of the NO2 and N2O4 can be sampled at any time. And this is the point when the system has reached equilibrium. Okay, so if let's say the concentration is sampled at this intercept point, so that the Q value or the reaction quotient value will not equal to the equilibrium constant value, because at this time the system is not at the equilibrium. However, if the Q is sampled, if the concentration is sampled starting at any point starting from this point, okay, then the value of Q will be equal to K, because starting from this point the system has reached equilibrium. So there are three possibilities condition for Q. It's either Q is less than K, or Q is greater than K, or Q is equal to K. So if the Q is less than K, so the Q need to increase until it is equal to K. To do so, the product concentration must be increased and the reactant concentration must be decreased. Therefore, the system is progressing towards the product side or to the right side. However, if the Q is greater than K, so the Q value will need to be decreased until it is equal to K. This can be happen by decreasing the concentration of the product and increasing the concentration of this reactant. Therefore, the system is progressing to the reactant side or to the left side. However, if we have a Q value that is equal to K, means that at this time the system is already at equilibrium, so no further net changes will occur. This figure also shows us the reaction quotient value is equal to the Kc value, means that no further changes occur because the system is already at the equilibrium. However, if the Qc is less than Kc, means that the Qc value need to be increased. Then to make it increase, the reaction progressing to the right and produce more product. However, if the Qc value is greater than Kc, the system is also not at the equilibrium, so the Qc value need to be decreased until it is the same as the Kc. So to do so, the reactant's concentration need to be increased, so the reaction is progressing to the left at this moment. So let's look at sample problem 17.1. This is how we want to write the reaction quotient's expression from the balance equation. So it is actually the same as when we write the Kc expression. It is actually the ratio of the concentration of the products of a reactant. And we look at to the first equation. 1 N2O5 produce 1 NO2 plus 1 oxygen gas. So before we write the QC expression, we have to make sure that our equation is a balanced equation. From what we have observed that this is not a balanced equation, so first step is to balance it. So this is the balanced equation. The QC expression is equal to NO2 concentration power of 4, O2 concentration power of 1 over N2O5 concentration power of 2. Same goes with the question B. First step is to balance the equation. So this is our balance equation. And the QC expression is equal to the concentration of the CO2 power of 3 multiply with the concentration of the H2O power of 4 divide with the concentration of the C3H8 power of 1 multiply with the concentration of the oxygen power of 5. This is how we write the reaction quotient. So if let's say we have to calculate the QC value, we just plug in the value. Okay, let's move to the second sample problem. Comparing the Q and the K value to determine the reaction direction. We have this decomposition reaction of the N2O4. The Kc is given as 0.21 and this reaction is happen at 100 degrees C. So at a point during the reaction, the concentration of the N2O4 is 0.12 molar and the concentration of the NO2 is 0.55 molar. At this time, when they sample the concentration of both of these two components, we are not sure whether the system is already at the equilibrium or it is not at the equilibrium. Then the question asks us to determine either the system is at the equilibrium or it is not at the equilibrium yet. And if it is not at the equilibrium, we have to identify which direction the reaction is progressing. Okay, so how to solve this problem? Firstly, we have to calculate the QC. Because only from the QC value that we know that either the system is at the equilibrium or it is not at the equilibrium. So the QC expression is equal to the concentration of the NO2 power of 2 divided with the concentration of the N2O4 power of 1 is equal to the values of the concentration that is given to us. 0.55 is the concentration of the NO2 power of 2 divided with 0.12 power of 1. Then we'll get the value of the QC is 2.5. Then we have to compare the value of the QC that we have calculated with the value of the Kc that is given. 2.5, compare it with 0.21. Then we know that our QC is greater than Kc. When QC is greater than Kc, means that the reaction is not at the equilibrium. And if the reaction wants to achieve the equilibrium to have the same value of Kc, then the reaction needs to proceed from right to left, or the reaction is progressing to the left to produce more reactant until the QC is equal to Kc. So after this, we'll discuss on the equilibrium problem. This is the mathematical parts of this topic. Stay tuned.